There is a moment, somewhere between silence and static, when our planet stops being just a rock spinning quietly through the dark and becomes something else entirely. Target, a receiver, a living antenna for a storm that began 93 million miles away on the surface of a star we call the Sun. Right now, that storm is coming. Scientists are calling it a G5. In the language of space, whether that is the highest number on the scale, the rarest, the most extreme, the kind of event that happens only a few times in a decade. Alongside it, something called the K-index, a number that measures how violently Earth's magnetic field is being shaken, is expected to spike into the red zone. Not orange, not yellow, red, the color reserved for chaos. To understand why this matters, you have to go back to where it all begins. Not on Earth, but on the Sun itself. The Sun looks calm from 93 million miles away, a steady golden disk. But up close, it is anything but peaceful. It is a boiling ocean of plasma, a sphere of hydrogen and helium so hot that atoms are torn apart, their electrons ripped free, leaving behind a churning soup of charged particles. And running through that plasma is something invisible but immensely powerful. A magnetic field, twisted and knotted by the Sun's rotation, wound tighter and tighter like a rubber band about to snap. Sometimes it snaps. When it does, the result is called a coronal mass ejection, a CME. Imagine an explosion the size of dozens of Earths, hurling billions of tons of magnetized plasma into space at speeds that can exceed 2 million miles per hour. It is, without exaggeration, one of the most violent events in our solar system. And when one of these eruptions happens to point directly at Earth, we call it an Earth-directed CME. That is exactly what has happened. Somewhere on the Sun's surface, a sunspot, a dark, cooler region twisted by intense magnetic activity, became unstable. Magnetic field lines crossed, tangled, and reconnected in a violent release of energy. In an instant, a flare of light brighter than anything on Earth erupted outward, followed by a colossal wall of solar plasma, launched directly toward us. It takes that wall of energy anywhere from 1 to 3 days to cross the gap between the Sun and Earth. And when it arrives, it doesn't just pass by. It collides with our planet's magnetic field, the invisible shield that has protected life on Earth for billions of years. That shield is called the magnetosphere. Most people never think about it, never see it, never even know it exists. But it is, quite literally, the reason life on Earth is possible. Generated deep within our planet's molten iron core, the magnetosphere stretches far out into space, deflecting the relentless stream of charged particles that flow from the Sun every single day, the solar wind. Without it, Earth's atmosphere would have been stripped away long ago, the way it was stripped from Mars. But when a CME hits, a wave of solar plasma far more intense than the ordinary solar wind, the magnetosphere doesn't just deflect it quietly. It gets compressed. It gets shaken. It rings like a bell struck by a hammer. This is a geomagnetic storm. And a G5, the strongest classification there is, means the collision will be severe enough to disturb systems we depend on every single day, systems most people never think about until they stop working. Let's start with the sky itself. During a G5 storm, the aurora, that shimmering curtain of green, red, and violet light usually reserved for the Arctic and Antarctic, can spread astonishingly far from the poles. In past G5 events, people in Florida, Texas, and even parts of Mexico have looked up and seen the northern lights dancing overhead, something that should be geographically impossible under normal conditions. It happens because the storm pushes so much energy into the upper atmosphere that the auroral oval, the ring of light around the magnetic poles, swells outward, sometimes reaching latitudes that haven't witnessed such a sight in living memory. For most people, this will be the beautiful side of the story. A rare, breathtaking light show, visible from cities that never see it. A natural spectacle trending across every phone screen in the country. Photographers will chase it. Families will stand in backyards at midnight, phones raised, watching colors ripple silently across a sky that, for one night, doesn't look like Earth's sky at all. But behind that beauty is a far less poetic reality. Because the same energy painting the sky red and green is also surging through Earth's magnetic field, and anything on the ground designed to conduct electricity is, in a sense, plugged directly into that disturbance. Consider the electrical grid. Power lines stretch for thousands of miles across the continent, forming enormous conductive loops. When Earth's magnetic field is violently disturbed, it induces electrical currents in those lines. Currents the system was never built to handle. These are called geomagnetically induced currents, or GICs. In smaller storms, this is a non-issue. But in a G5 event, these currents can be strong enough to overload transformers, the massive, expensive pieces of equipment that step electricity up and down as it travels through the grid. This isn't theoretical. In March 1989, a geomagnetic storm of similar intensity hit Earth and knocked out the entire power grid of Quebec, Canada, in under 2 minutes. 6 million people lost electricity in the middle of winter. Transformers as far away as New Jersey were damaged by the surge. It was a stark demonstration that a storm 93 million miles away could black out cities on Earth in the time it takes to boil an egg. Now scale that concern up to a G5, and you understand why power companies across the world are watching this event with intense focus, running protective protocols, and in some cases deliberately taking portions of the grid offline to prevent damage before the storm even arrives. But the grid isn't the only system at risk. High above our heads, thousands of satellites quietly orbit the planet. GPS satellites, communication satellites, weather satellites, the invisible infrastructure of modern life. During a geomagnetic storm, the upper atmosphere heats up and expands. This might sound harmless, but for satellites in low Earth orbit, it means increased atmospheric drag, like trying to fly a plane through suddenly thicker air. Orbits can decay faster than expected. In February 2022, a G5 adjacent storm was directly responsible for the loss of dozens of newly launched satellites, which fell out of orbit and burned up in the atmosphere within days, their trajectories disrupted before they could even reach a stable altitude. Then there's GPS. Nearly everything in modern life quietly depends on GPS. Not just navigation apps, but banking systems, agricultural equipment, shipping logistics, and cellular network timing. During intense geomagnetic storms, the ionosphere, the electrically charged layer of Earth's atmosphere that GPS signals travel through, becomes disturbed and scrambled. Signals can be delayed, distorted, or lost entirely. Precision farming equipment, which relies on GPS accuracy down to inches, may become unreliable for hours. Some shipping and aviation systems could see temporary disruptions in positioning accuracy. Speaking of aviation, airlines flying polar routes, the shortest paths between North America and Asia, often reroute flights during severe geomagnetic storms. This isn't just caution. It's because high-frequency radio communication, essential for polar flights where satellite communication can be unreliable near the poles, becomes degraded or unusable during intense solar storms. Passengers and crew on polar routes are also exposed to slightly higher levels of radiation during these events, which is one of the quiet reasons airlines take rerouting seriously. And it doesn't stop there. Radio communications on the ground, used by emergency services, ham radio operators, maritime vessels, and the military, can experience blackouts, particularly on the sunlit side of Earth where the ionosphere is affected first and most severely. It's worth pausing here to say clearly, this is not a doomsday scenario. Life will go on. The sun rises, storms pass, and the systems that fail during a geomagnetic storm are, for the most part, repaired or restored within hours to days. But it is a genuine reminder of something we rarely think about, how deeply modern civilization depends on invisible, silent infrastructure that can be disrupted by forces older than humanity itself. So what actually happens, hour by hour, as a storm like this unfolds? It begins quietly. Space weather satellites, positioned about 1 million miles from Earth at a gravitational balance point called Lagrange Point 1, detect the leading edge of the CME as it approaches. These satellites act as an early warning system, giving scientists anywhere from 15 minutes to about an hour of advance notice before the wave of plasma actually strikes Earth's magnetic field. It's not much time, but it's enough for power grid operators to take protective action, enough for satellite operators to put spacecraft into safe mode, enough for airlines to adjust flight paths. Then impact. The solar wind, ordinarily flowing at around 250 miles per second, might suddenly surge to speeds several times that. Earth's magnetic field compresses on the side facing the sun, sometimes shrinking from its normal boundary of about 40,000 miles above Earth down to a fraction of that distance. The magnetosphere shudders. Electric currents begin flowing through the ionosphere and down into the ground, energy pouring into the upper atmosphere in the form of light, the aurora, and heat, causing the atmosphere to expand. The K-index, that number scientists watch so closely, begins to climb. A K-index of 5 is considered a minor storm. A K-index of 9, the maximum on the scale, corresponds to the most extreme conditions, a truly red alert level disturbance. When forecasters say the K-index is expected to reach red levels, they are describing conditions capable of producing all of the effects we've discussed: grid strain, satellite drag, GPS disruption, radio blackouts, and auroras visible far beyond their usual home near the poles. This state of disturbance can last anywhere from several hours to a couple of days, gradually easing as the CMEs energy passes by and Earth's magnetic field slowly settles back into its normal rhythm, like the surface of a pond returning to stillness after a stone has been thrown in. It's tempting to think of this as something that only affects power companies and satellite engineers, far removed from everyday life. But geomagnetic storms have a strange way of surfacing in unexpected corners of daily existence. Homing pigeons have been documented losing their sense of direction during major solar storms. Since some animals appear to use Earth's magnetic field for navigation, compasses can show slightly inaccurate readings. Even some old theories about correlations between space weather and technology failures, once dismissed as folklore, have gained more serious scientific scrutiny as researchers better understand the true reach of these events. And there is something almost humbling in that. For most of human history, our ancestors had no idea that the sun could do this, that a star so far away, so seemingly separate from our daily lives, could reach across the vacuum of space and shake the ground beneath our feet, disturb the compass in our pocket, paint the sky in colors that don't belong there. It was only in the last couple of centuries that we even began to understand the connection, and only in the last few decades that we've built the tools to see it coming. That, in the end, may be the most important part of this story, not the storm itself but our growing ability to forecast it. Just a generation ago, an event like this would have arrived with almost no warning, a sudden and mysterious wave of blackouts and radio silence that no one could explain in the moment. Today, satellites watch the sun continuously. Scientists model the trajectory of these eruptions with increasing precision, and warnings are issued days in advance, giving governments, power companies, and airlines time to prepare. So as this G5 storm approaches, and as the K-index climbs into the red, what should the average person actually expect? For most people, in most places, the honest answer is very little disruption to daily life. Perhaps a flicker in internet connectivity. Perhaps a GPS app that seems slightly off for a few hours. Perhaps, in rare cases, a brief regional power fluctuation, especially in areas with older grid infrastructure. But for the vast majority of people, the most noticeable effect will be the one that requires no equipment, no warning system, no scientific instrument at all. Simply the choice to step outside after dark and look up. Because if the storm behaves as forecasters expect, the aurora may descend far from its usual home, painting skies over cities that haven't seen it in decades, maybe longer. Green and red light rippling silently overhead, a reminder that we live not in isolation, but inside the reach of a star 93 million miles away. A star that occasionally exhales, and in doing so, touches every part of the world we've built. That is, in many ways, the quiet truth hidden inside every geomagnetic storm. We tend to think of the sun as a fixed and simple presence, rising, setting, warming the Earth in exactly the same way, day after day, year after year. But the sun is not static. It breathes, it erupts, it sends waves of energy rippling outward in every direction. And every so often, one of those waves finds us directly in its path. When that happens, our planet responds the only way it can, not by breaking, but by ringing briefly, like a bell struck in the dark. Power grids strain, satellites drift, radios fall silent for a moment, and far above it all, the sky ignites in colors most of us will never forget. And then, as it always has, the storm passes, the magnetosphere settles, the grid stabilizes, the satellites correct their orbits, the auroras fade back toward the poles where they belong, and life on Earth, resilient, adaptive, and largely unaware of just how close it flirts with the raw power of its own star, continues on, exactly as it has for billions of years. Because in the end, this is not a story about disaster. It is a story about connection. A reminder that Earth does not exist in silence, separate from the universe around it, but is instead in constant, invisible conversation with a star 93 million miles away. A conversation written not in words, but in light, in magnetism, in the quiet hum of a planet absorbing the breath of its sun. And for one night, if the forecasts hold true, that conversation will be visible to all of us, written across the sky in red.